Hello everyone, this is the solution to quiz 0. Now the task was to implement the function tf to sim, which just accepts a transfer function object of the control system toolbox in MATLAB and returns the symbolic fraction that corresponds to the same transfer function, but of course in symbolic toolbox, in the symbolic toolbox. Now we're not allowed to use any basic MATLAB code built-in functions that already does this, and the grading is divided into two. First, you are asked for a SISO version. So if you just implement the SISO version, you get 50 points. If you also manage to code the MIMO version, multiple input, multiple output transfer function version, then you get 50 points more, which adds up to 100. Now, I might have talked about this function before, which is a very basic one, actually. So let's dive into it. Now you were provided a template function here. You should just implement it in here and submit it, and that would be it. Now, first of all, what we need is we need the symbolic variable s that we use all the time. Now, it is possible to get the size of GS, even if it's a transfer function object. We most of the time do it with matrices and vectors. We do size, and then we provide a certain vector, for example, and we get the size. It is a 1/2 vector, for example. It is also possible to do the same with transfer functions. So let me just show you a transfer function that is a MIMO transfer function. You can just stack transfer functions like a number in a vector. For example, if we have this here and maybe 1 to 4, you can just define transfer functions like this. You can see it is a MIMO. In fact, we have 2 inputs and just 1 output. It shows you that. Therefore, I can also use size on this. So let me just take this. Let me just create a test.m file here, which you were not given, which is just for testing purposes. So there we go. And then I want to just call sim to tf, provide the function, and get hopefully the symbolic representation here. Now, if I call the main function here, the test function here, hope that MATLAB reacts. There we go. We've just that, and the it is tf to sim. I'm sorry. tf to sim makes more sense, of course. So let's run it. It does nothing, returns nothing. Therefore, we get an error because we just assumed, or MATLAB assumes that we will return GSS, but it's not already defined, so it is not assigned, so it throws an error. Now, I can take the size. I've talked about this. So m and let's use size gs, and it should return what m is and what n is. I'm directly diving into the MIMO application here. You can see that I have 1 row and 2 columns. So of course it's possible to do the same here like a matrix. You can just use a semicolon. Maybe copy and paste this to have a 2 input to output system. Let's change it to another thing here. For example, 7, 0. I don't know. I'm just making them up. So there we go. You can see we have 1 input to the output, the first input to the output, the second input to the output, and of course there are also multiple outputs here. So if I look at GS, that's basically it. And if I look at the size of GS, which is already in M and N, it's a 2/2. So now, how can we deal with such transfer functions, and how can we convert them into symbolic expressions? Well, we have M and N, and if we want to extract the corresponding input to output channel in a MIMO system, what we can do is we can just use the numerator and denominator, And most of the time when we use the numerator, for example, so let me just let me also assign this to equal to 1. If I look at the numerator of the transfer function, you can see that it gives me a cell array of the according size. So I have m and n. I know that it is a 2 by 2 transfer function matrix. And I also see that accessing the numerator here gives me the same structure here. So I can access all the numerators that correspond to the input and output channels that are available on this transfer function. So what I can do is I can just use 2 for loops, one for the row and one for the column, and access the numerator corresponding to that. So what I mean by that is the following. Let's have for I equals 1 to m, and then for j equals 1 up to n. And since it's a cell array, I can just use this curly bracket here and call I comma j. So the ith row, jth column of this numerator, which will correspond to basically, if it's 1 by 1, it would be this one here. If it's 1, 2, this one would be invoked, 2, 1, and 2, 2. So let me just again call the test function here. Maybe run it again. There we go. Now we see that we have 0, 1, which is the numerator of the first input to output. And then we have 0, 2, which is basically the second one here. And then we have 0, 0, 1 and 0, 0, 1, which are basically these here. Of course, I need also the denominator, so I can also do the same for the denominator. So let me again run tests. There we go. We have the numerators, denominator. So the first one is 1 divided by s plus 1. The second one is 2 divided by s plus 4, which is this one here. And then we have 1 divided by s squared plus 3s plus 1, which is this one here. And of course, 1 divided by s squared plus 7s. Seems like we're done. So it's the second task here was basically to implement the SysO version and then wrap it in a for loop like this. Once you have done that and store it again back in GSS, you should be good to go. Now let's focus on this part here. Let's say we have the numerator, which is this, and the denominator. Let's save them to certain variables. Now at this point, I can also create a GSS that should be a variable, that should be a matrix, and I should return this. So this will hold my result here, and I know that I can just use m by n, which would be the size that is necessary in this case. So let me show you the result of this. There we go. It's a zero matrix, 2 by 2, because we have 2 inputs and 2 outputs. But the problem here is the following. If I, for some reason, want to assign GSS, the first element of this, to 1 divided by s, let's assume that. If I hit run one more time, I can see that it has a trouble. And the problem here is that I have allocated GSS using zeros, which is basically not a symbolic data at all. But then I try to fit in the symbolic data into its first row, first column. So I cannot assign something that is not symbolic to a symbolic result. So sometimes in MATLAB, and only in MATLAB, you can just get away with the following. And if you add more stuff, it will reallocate it and do it. So if you just use ij in the for loop, it should be good. But I like to use pre-allocation here. And remember that we are using the double function in order to convert stuff into double. There is also the same for sim. You can just provide any number to sim, and it will just directly give you the symbolic version here. So you can see it's 1 divided by 2, not 0.5, as you can see. And it is a symbolic variable here. So I can wrap this into a sim function or convert it into symbolic so that it is possible now. Of course, you don't have to pre-allocate, as I've talked about it. Now I can assign symbolic stuff into this matrix here, which is symbolic. If you are using the MATLAB IDE, you would see in the workspace that this is a symbolic variable. So sim 2x2 sim, something like that would pop up there. But yeah, you don't really have to pre-allocate it. You can just assign it in a for loop. That is the flexibility of MATLAB. But I like to keep things pre-allocated so I know what I'm doing. So yeah, this is more efficient in my opinion, but you don't really have to do this. So now the only thing that remains here is to just convert the stuff. Now we are going to do the following. First of all, we need to calculate the order of the system. And the best way of doing this is to look at the, for example, we have then, if it's still living there, no. Let's see what the last value here was. You can see that this is a vector that holds the denominator of the last transfer function that we've addressed. Now we can use actually the length here, since this is a polynomial and it will have the constant term plus the powers from 1 to n. So there will be n plus 1 coefficients in this. So if I count the coefficients, subtract 1, that should give me the order of the system that I'm interested in. So length of the denominator minus 1 because we have the constant term. So it goes from 0, 1 to up to n. Therefore, we have n plus 1 coefficients. I have to subtract 1 from the length in order to get the number n. In this case, we have 3 coefficients. Subtract 1 gives you 2. It is a second order transfer function. So once you have calculated that, you need just 2 polynomials that will be symbolic, like this. And then we have to somehow come up with a way of indexing each coefficient. Well, we will use a for loop, let's say k from 1 to length then. So we will address all the coefficients in the denominator in this case. You can also plug in n plus 1, but length then works also because it's the same. Now what we really have to do in this case is that we have to remember that the first element, if k is equal to 1, the first element of the denominator vector is going to be this one here. And this should be the highest order term of s. So I'm going to multiply it with s, and I need the power, and it will not be k because k is equal to 1. I need to use this n here, n, but then again it will not be always n. As k increases, as I'm going through each element here, I'm decreasing in the order of s. So I should subtract k from it. So n minus k. But the problem here is that if k is equal to 1, then the first term will be then 1. So let me write it down. Then 1 times s to the power of n minus 1. Now that's not correct. So in order to correct this, I have to add 1 to it. So it will get rid of this starting point and correct it so that it will be equal to s to the power of n. And as k increases, it will be then 2, n minus 1, then 3, n minus 2, etc. And when we're done, we should get basically s to the power of 0, which will be the constant term, and you will add the constant term to the polynomial. So this seems to be correct. Let's add ns. It's the denominator, so let's add ds plus ds, this term here, so it kind of generates the polynomial on the go. Num, and there we go. The only thing that will be left here is to just go to the ith, jth element, assign ns divided by ds, and that should be it. Now the problem here is, of course, I have already used n, so it's m by n. If I want to use the order, I can maybe use n underscore to define another variable that is also called n, but it's not exactly n. So the nth, or you can also call it order, but I'd like to stick with n because it is kind of self-explanatory at this point. So yeah, this should be it actually. Let's try it out first. We have assigned it, yep. So let's try it out one more time. There we go. Now you see that 1 divided by s squared plus 7s is here, and 3s plus 1 is here, and then 1s plus 1, 2s plus 4. It's basically the same. If I write it down like this, you'll see that it is the same here. Yeah, if you provide a single input, single output transfer function, it should also work. Let's test that out. But it seems like it is not even relevant to try it out because if it's a CISO one, it should also work. It's kind of obvious at this point. Because the for loop vanishes, it is 1 and 1, and you're just assigning 1. So let's us get rid of that, and let's see if it's still working here. As you can see, you can do that in MATLAB. You can just not define GS, but if you're in a for loop, if you're just assigning stuff, it will just create the memory and grow it as it's needed. But I'd like to fix the memory usage here because you're copying the same stuff, moving it, or MATLAB kind of handles it behind the scenes. But yeah, a static definition is better in my opinion. Now this is basically the implementation that was asked for. Let me just recap. We have a transfer function matrix as an input. We get the symbolic representation. Now, how do we do that? We define the symbolic variable s. We get the size of the transfer function matrix, which is quite important. We define the corresponding symbolic fraction matrix. And then we use m and n. We cycle through each element and we assign basically we get the numerator coefficients and the denominator coefficients. We compute the order of the system, which is based on the characteristic polynomial, the length of it, subtract 1, because we have a constant term, we get the order n. We create two dummy variables here for the polynomials, ns, the numerator s, and denominator s, and we cycle through each element in the denominator. We multiply them with the corresponding order, which is n, the order, minus k, plus 1, because k starts at 1. We should get rid of that, because we will start with n. And if that's if k is equal to n minus 1, I guess, it should give us a constant term here. N plus 1, because we have n plus 1 here. N minus n minus 1 plus 1 should give us 0. S to the power of 0 is the constant term. And then we just define a fraction. Now we have converted a transfer function matrix into the symbolic expression. So this is basically the solution here. Yeah, this is the CISO and MIMO solution of TF to SIM. Of course, you can come up with SIM to TF, which is basically the same. You again use the coefficients. This time you will use numdan, but then you have to check the size of the matrix and then numdan, and then pre-allocate that stuff as a TF and then assign it. But it is kind of the same idea, and it is easier to come up with SIM to TF than TF to SIM, if you ask me. So hope that was helpful. See you in the next video.